Fundamentals of Digital Electronics, Logic Gates and Designing of Adder Circuits using Logic Gates. This module is aimed to provide an introduction of logic gates and designing of simple logic circuits capable of performing arithmetic additions of binary numbers to the first year undergraduate students of BSc Physical Sciences program. An elementary understanding of the binary number system, binary addition, Boolean functions and expressions is required in order to proceed further with the contents of this module. As we all know, all the digital systems of modern times are based on logic systems. Let us now understand how to transform from a digital system to a logical system. This can be done by drawing an analogy between the corresponding terms in the two. For example, high and low voltage levels in a digital circuit correspond to logic levels 1 and 0 in a logic circuit. These logic systems in turn consist of logic gates. Now the question arises, what is a logic gate? Well, we can say logic gate is an electronic circuit capable of implementing specific Boolean functions. For example, AND gate can implement the Boolean function A into B. A gate can have one or more than one input signals represented by logic levels having only two binary values, that is 0 and 1. The number of outputs is, however, restricted to 1 only. Now, the logic levels representation of high and low voltage levels in any logic circuit is of two types. 1. Positive logic. If high voltage level is represented by 1 and low voltage level is represented by 0, then the logic system is said to be based on positive logic. 2. Negative logic. If high voltage is represented by 0 and low voltage level is represented by 1, then the logic system is said to be based on negative logic. Among the various gates, there are three basic gates, which, in principle, can be used for designing any logic circuit. These are NOT gate, AND gate, and OR gate. Using the three basic gates AND, OR, and NOT, more gates can be constructed. These are NOR gate, NAND gate, XOR gate, and XNOR gate. Each gate is represented by a distinct logic symbol and its operation can be represented by a Boolean function. Among all the gates, NOT is the only gate which has single input. All the other gates have two or more than two inputs. If a gate has two inputs A and B, then in binary number system 2 raised to power 2, that is 4 distinct combinations of inputs are possible. For 3 inputs gate 2 raised to power 3, that is 8 combinations of inputs are possible. Similarly, for n inputs 2 raised to power n combinations of inputs are possible. The 4 distinct input combinations for a 2 inputs gate are A equals 0, B equals 0. A equals 0, B equals 1. A equals 1, B equals 0. And A equals 1, B equals 1. Likewise, the 8 distinct combinations for 3 inputs gate in order of A, B, and C are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. This process can be extended to any higher number of inputs, and in principle, for n inputs, we have 2 raised to power n number of input combinations in terms of binary digits 0 and 1. Now the output of a logic gate depends on the nature of the gate and is unique for each type of gate. A table depicting the output for different possible inputs A, B, C, etc. can thus be written for each type of gate. This table is called truth table. Now from this point onwards, we shall discuss the various gates one by one. The first and the most elementary gate is the NOT gate, which is a single input gate. The Boolean function for NOT gate is B is equal to A bar. Being a single input gate, the truth table for NOT gate has only 2 raised to power 1, that is 2 combinations, 0 and 1. When A is equal to 0, B equals to 1, and when A is equal to 1, B equals to 0. What do you understand from this? That is, B is complement of A. The logic symbol of NOT gate is represented by a triangle with input A connected to one of its sides and bubble placed on the opposite vertex. The output B then emerges from this vertex. The bubble at the output signifies the inversion of the input A to A bar. Thus, the output B is equal to A bar. Next is the AND gate. AND gate is a 2 or more inputs gate. The Boolean function for AND gate is C equal to A into B. The characteristic feature of AND gate is that the output C is 1 only when both the inputs A and B are 1. If either or both inputs are 0, the output is essentially 0. As we understood earlier, in the truth table of a 2-input AND gate, there will be 4 input combinations. For inputs 0, 0, the output is 0. For inputs 0, 1, the output is 0. For inputs 1, 0, the output is again 0. For inputs 1, 1 only, the output is 1. Similarly, for 3 inputs AND gate, the Boolean function is B equals to A into B into C. The output D is 1 only if all the inputs A, B and C are 1. If any of the inputs is 0, the output is 0. Now let's describe the truth table of 3 inputs AND gate. For 0, 0, 0 inputs, the output D is 0. For 0, 0, 1 inputs, D is 0. For 0, 1, 0 inputs, D is 0. For 0, 1, 1 inputs, D is again 0. For 1, 0, 0 inputs, D is 0. For 1, 0, 1 inputs, D is 0. For 1, 1, 0 inputs, D is 0 again. For 1, 1, 1 inputs, D is 1. Thus, in the truth table for 3 inputs AND gate, the characteristic feature of AND gate, that is the output is 1 only when all the 3 inputs are 1, is clearly visible. Likewise, the idea of 3 inputs can be extended further to 4, 5, 6 till n inputs. Clearly, the output is 1 only when all the inputs A, B, C, D, etc. are 1. If any of the inputs is 0, the output is essentially 0. The logic symbol of AND gate is somewhat D-shaped, with the inputs A and B connected to the flat side and the output C being connected to the opposite outwardly convex side of the D shape. The output C equals to A into B. Accordingly, we can have 3 inputs and n inputs AND gate. Let us now discuss the last basic gate, that is OR gate. OR gate is also a 2 or more inputs gate. The Boolean function for OR gate is equal to A plus B. The characteristic feature of OR gate is that the output C is 1 when either A or B or both the inputs A and B are 1. If both the inputs are 0, then only the output is 0. The truth table for 2 inputs OR gate reads like this. For 0, 0 inputs, the output C is 0. For 0, 1 inputs, the output C is 1. For 1, 0 inputs, the output C is 1. For 1, 1 inputs, the output C is still 1. One can note that output is 1 in all cases except when both the inputs are 0. Similarly, we can have 3 inputs OR gate, and the Boolean function for this will be D equals to A plus B plus C. And the output D is 0 only if all the inputs A, B and C are 0. If any of the inputs is 1, the output is 1. Accordingly, one can write the truth table for a 3 inputs OR gate as well. One can note that the output is 1 for all the cases except when all the inputs are 0 in all the 8 distinct combinations. Likewise, the idea can be extended to n inputs, with the Boolean function being A plus B plus C plus and so on, and output being 0 only if all the inputs A, B and C are 0. If any of the inputs is 1, the output will be 1. Now the logic symbol of OR gate can be visualized as V shape of AND gate with its flat input end being somewhat concave. Similarly, we can have 3 and more inputs OR gate by joining additional number of inputs. So far we have discussed the basic gates AND, OR and NOT. Now we will familiarize ourselves with the other gates like NOR, NAND, XOR and XNOR gates and try to understand how these can be constructed using AND, OR and NOT gates. First, let us take NOR gate. As the name suggests, the output of NOR gate is complement of the output of an OR gate. This means the Boolean function for NOR gate is C equals to A plus B whole bar. NOR gate is also a 2 or more input gate. Since the output of a NOR gate is complement of an OR gate, it can be constructed by connecting the output of a NOR gate to the input of a NOT gate. That is, the output of a NOR gate A plus B is connected to the input of a NOT gate, and the output of the combination is now A plus B whole bar. This combination of OR and NOT gate is depicted in the form of the logical symbol for NOR gate by showing a bubble at the output end of the logic symbol for OR gate for denoting the inversion. Now, the truth table for NOR gate reads out to be for inputs AB to be 0, 0, the output C is equal to 1. For inputs AB equal to 0, 1, the output C is equal to 0. For inputs 1, 0, the output C is equal to 0. For inputs 1, 1, the output is 0. We may again note that the output C is 1 only when both the inputs are 0. If either A or B or both are 1, then the output is 0. As for previous gates, we may have 3 inputs NOR gate as well. The Boolean function for 3 inputs NOR gate can be written D equals to A plus B plus C whole bar. The output D is 1 only if all the inputs A, B and C are 0. If any of the inputs is 1, the output is 0. And the truth table reads as for A, B and C equal to 0, 0, 0, D is equal to 1. For A, B and C equal to 0, 0, 1, the output D is equal to 0. For A, B, C equal to 0, 1, 0, D is equal to 0. For A, B, C equal to 0, 1, 1, D is equal to 0. For A, B, C equal to 1, 0, 0, D is equal to 0. For 1, 0, 1 inputs, D is equal to 0 again. For 1, 1, 0 inputs, the value of output is still 0. For 1, 1, 1, D is again equal to 0. Thus, the output is 0 in all cases except when all the 3 inputs are 0. The idea of 2 and 3 inputs, as we understood earlier, can be extended to more inputs, say n inputs. The Boolean function for n inputs NOR gate will be a plus b plus c plus d and so on, whole bar. The output d will be 1 only if all the n inputs a, b, c and d etc. are 0. If any of the inputs is 1, the output is 0. Now we will understand that a NOR gate is equivalent to a bubbled AND gate. As we know, the output of a NOR gate is a plus b whole bar. According to De Morgan's first theorem, a plus b whole bar is equal to a bar into b bar. Now, if both the inputs a and b are complemented using two NOR gates, before ANDing them, the output will be a bar into b bar, which in turn equals to a plus b whole bar. Thus, a NOR gate is equivalent to a bubbled AND gate. Logically, this means we connect two NOR gates to complement the inputs a and b to a bar and b bar respectively. Then AND the complemented inputs. The output is now a bar into b bar. This, according to De Morgan's first theorem, is equal to a plus b whole bar, which is nothing but the output of a NOR gate. Thus, an AND gate with NOT gate connected to each input makes into a NOR gate. This is usually denoted by putting two bubbles at the input end of an AND gate, where the bubble signifies the inversion of inputs. Let us now move to the next gate, that is NAND gate. The Boolean function for NAND gate is C is equal to A into B whole bar. That is, the output of a NAND gate is equal to the complement of the output of an AND gate. Thus, a NAND gate can be constructed by connecting a NOT gate to the output of an AND gate. Let us now construct NAND gate using AND and NOT gates. For this, we connect the output A into B of an AND gate to the input of a NOT gate. The output is now A into B whole bar. This combination of AND and NOT gate is represented by the logic symbol of NAND gate, which is formed by putting a bubble at the output of an AND gate to denote the inversion. The truth table of a NAND gate reads for inputs A and B as 0, 0. The output C is 1. For inputs 0, 1, the output C is 1. For inputs 1, 0, the output C is 1. For inputs 1, 1, output C is 0. One may again know that the output is always 1 except the case when both the inputs are 1. Similarly, the Boolean function for 3 inputs NAND gate is D is equal to A into B into C whole bar, and the output D is 0 only if all the inputs A, B and C are 1. If any of the inputs is 0, the output is 1. Now let us write the truth table for 3 input NAND gate. For inputs A, B, C 0, 0, 0, the output D is 1. For 0, 0, 1, the output is 1. For 0, 1, 0, D is 1. For 0, 1, 1, D is 1. For 1, 0, 0, D is 1. For 1, 0, 1, D is 1. For 1, 1, 0, D is 1. For 1, 1, 1, D is 0. Likewise, we may have n inputs NAND gate. We earlier saw that a NOR gate is equivalent to a bubbled AND gate. In a similar manner, one can understand that a NAND gate is equivalent to a bubbled OR gate. We know the output of a NAND gate is A into B bar. According to De Morgan's second theorem, A into B bar is equal to A bar plus B bar. Now, if both the inputs A and B are complemented using two NOT gates, before ORing them, the output will be A bar plus B bar, which is equal to A into B bar. Thus, a NAND gate is equivalent to a bubbled OR gate. Let us now construct a NAND gate using AND NOT gate. For this, use two NOT gates to complement the inputs A and B to A bar and B bar respectively. Then, OR the complemented inputs A bar and B bar. This inversion of inputs A and B before ORing them is represented by putting two bubbles at the inputs of the OR gate. The output of the combination is A bar plus B bar, which according to De Morgan's second theorem is equal to A into B whole bar. Thus, we get a NAND gate with the output being A into B whole bar. Next is an exclusive OR, that is XOR gate. The Boolean function for XOR gate is also represented as C equals to A XOR B. The output C is 1 in those cases exclusively when either input A or input B is 1. Hence the name. The truth table for XOR gate for two inputs A and B reads like this. For inputs 0, 0, the output C is 0. For inputs 0, 1, the output C is 1. For 1, 0, C is 1. For 1, 1, C is 0. It can be noted from the truth table that the output C is 1 only when either A or B is exclusively 1. This is precisely why we call it an exclusive OR gate. Now we will apply sum of product, that is SOP method, to the truth table of XOR gate and determine the Boolean function as A bar into B plus A into B bar, thus representing XOR gate in terms of basic gates. Let us derive the Boolean expression for the truth table of XOR gate using sum of product, that is SOP method, in the following manner. First, write fundamental product terms against each cell in the output column where C is 1. To write a fundamental product, the inputs A and B are taken in product. If any input is 0, it is taken in its complement form. For example, in the second row of the truth table, the output C is 1 for inputs A equal to 0 and B equal to 1. Thus, the fundamental product will be A bar into B. In this manner, we write all the fundamental product terms against each one in the output column. Then output C is equal to the sum of all such fundamental terms, and this is the Boolean function representing C. Now logic circuit can be designed for this Boolean expression. While designing a logic circuit for the Boolean expression derived earlier, following steps are taken. We place product terms in the Boolean expression with AND operation with the appropriate inputs. Wherever we have a complemented term in the Boolean expression, we use NOT gate to invert that particular input before ANDing it, or all the outputs of the AND gates to perform the summing operation in the Boolean expression. For example, for the first term in the Boolean expression for C, that is A bar into B, A has been inverted to A bar using NOT gate and then ANDed with B to obtain A bar B. Similarly, the second term, that is A into B bar, is translated into logic circuit. Then the output of two AND gates, that is A bar into B and A into B bar, are ORed using an OR gate. This method is appropriately called sum of product method because each output is first written as product and then summed over. Like all the other previous gates, XOR gate can also have more than two inputs, and the Boolean function for a 3-input XOR gate will then be D is equal to A XOR B XOR C. We shall see shortly that the output is 1 when the number of ones in the input is odd, otherwise it is 0. Let us now look at the Boolean function for 3 inputs XOR gate as B equals to bracket open A XOR B bracket close XOR C. Substituting various input values, we can write the truth table which is like this. For inputs A, B, C being 0, 0, 0, the output D is 0. For 0, 0, 1, D is 1. For 0, 1, 0, D is 1. For 0, 1, 1, D is 0. For 1, 0, 0, D is 1. For 1, 0, 1, D is 0. For 1, 1, 0, D is 0. For 1, 1, 1, D is 1. One can see from the truth table that the output D is 1 when the number of ones among the inputs A, B and C is odd. For example, when A is equal to 0, B is equal to 0 and C is equal to 1, the number of ones in the inputs is 1. That is odd. Hence, the output D is 1. Similarly, in the last row, the number of ones in the inputs is 3. That is, A is equal to 1, B is equal to 1, C is equal to 1. Hence, output D is 1. We can write fundamental product terms along with the output D in the same manner as described earlier. Now we shall apply SOP method to determine the Boolean expression for 3 inputs XOR gate. We can see from the truth table for a 3 inputs XOR gate, the fundamental product terms corresponding to D equal to 1 are A bar, B bar, C, A bar, B, C bar, A, B bar, C bar and A, B, C. Taking the sum of these fundamental product terms, we get Boolean expression for D, and that is equal to A bar, B bar, C plus A bar, B, C bar plus A, B bar, C bar plus A, B, C. Taking A bar common from the first and the second term, we can write D is equal to A bar into bracket open B bar C plus B C bar bracket closed plus taking A common from the third and fourth term, we can write A bracket open B bar C bar plus B C bracket closed. Now the term B bar C plus B C bar in the first term is nothing but Boolean expression for B XOR C. Thus, we can write D is equal to A bar bracket open B XOR C bracket close plus A bracket open B bar C bar plus BC bracket close. Now, we can show very easily that B bar C bar plus BC is nothing but B XOR C whole bar. This can be done in the following manner. Let us assume B XOR C is equal to Y. Then Y is equal to B bar C plus B C bar. Accordingly, Y bar is equal to B bar C plus B C bar whole bar, which in turn, using De Morgan's theorem, is equal to B bar into C whole bar into B into C bar whole bar. Using De Morgan's theorem, this is equal to B bar bar plus C bar into B bar plus C bar bar. Now we know B bar bar is equal to B, and similarly C bar bar is equal to C. Thus, we can write Y bar is equal to bracket open B plus C bar bracket close into bracket open B bar plus C bracket close. This is equal to B bar plus B C plus B bar into C bar plus C bar into C. Now the product of a number with its complement is 0. That is, B into B bar is equal to 0. C into C bar is equal to 0. Thus, Y bar is equal to BC plus B bar C bar. Coming back to the Boolean expression for D, using this we can write down D is equal to A bar Y plus A Y bar, which is nothing but A XOR Y, and substituting for Y equal to B XOR C, we write the Boolean expression for D, that is A XOR B XOR C. Now let us build the logic circuit for a 3-input XOR gate. It can be constructed by connecting the output of a 2-input XOR gate and the third input C to the input pins of second XOR gate. The output so obtained is the output of 3-input XOR gate. Extending the idea of 3 inputs to 4, 5, 6 and so on, say n inputs, Boolean function for n inputs XOR gate can be written as A XOR B XOR C XOR D XOR so on. The output is 1 when the number of ones in the inputs is odd, otherwise it is 0. We can visualize the logic symbol of an XOR gate as that of an OR gate with an additional arc parallel to the input concave side. XOR gate is a special gate in the sense that it has many applications because of its unique nature. These are comparing bits for dissimilarity, checking parity, controlled inversion of bits, arithmetic addition. Now the first feature is comparing bits for dissimilarity. This feature is based on the fact that the output C is 1 in those cases exclusively when input A and input B are dissimilar. This feature can be used for comparing any two bits at the inputs for dissimilarity. Checking parity. It can be seen from the truth table that when the number of ones in the inputs is odd, for example, in second, third, fifth and eighth row, the output D is 1. In other words, when the parity of the input bits is odd, the output bit is 1. This feature allows XOR gate to be used as parity checker of the data at the inputs. Controlled inversion of bits. We can see from the truth table that when A is equal to 0 and B is equal to 0, C is equal to 0. And when A is equal to 0 and B is equal to 1, C is equal to 1. Thus, C is equal to B in both the cases when A is 0. In other words, when input A is equal to 0, the other input, that is B, is transmitted unchanged to the output C. Also, we can see from the truth table that when A is equal to 1 and B is equal to 0, C is equal to 1. And when A is equal to 1 and B is equal to 1, C is equal to 0. Thus, C is equal to complement of B in both the cases when A is equal to 1. In other words, when input A is equal to 1, the other input B is inverted at the output C. Thus, XOR gate functions as a controlled inverter with one input, for example A, controlling the inversion of the other bit and vice versa. Arithmetic addition. From the truth table, we can see that the output C of an XOR gate is nothing but sum of input bits A and B. That is 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1, 1 plus 1 equal to 0. Let us confirm this feature for 3 inputs XOR gate as well. One can see that the output D is sum of input binary bits for 3 inputs XOR gate as well. That is, D is equal to sum of A, B and C. We can elaborate this. 0 plus 0 plus 0 is equal to 0. 0 plus 0 plus 1 is equal to 1. 0 plus 1 plus 0 is equal to 1. 0 plus 1 plus 0 is equal to 1. 0 plus 1 plus 1 is equal to 0. 1 plus 0 plus 0 is equal to 1. 1 plus 0 plus 1 is equal to 0. 1 plus 1 plus 0 is equal to 0. 1 plus 1 plus 1 is equal to 1. Thus, XOR gate can be used for arithmetic addition. Let us now discuss the last gate, that is XNOR gate. As the name suggests, the output of an XNOR gate is complement of the output of an XOR gate. Thus, the Boolean function for this gate is C equals to A XOR B whole bar. Let us now write the truth table for a 2-input XNOR gate. When A and B are 0, 0, C is 1. For 0, 1, C is 0. For 1, 0, C is 0. For 1, 1, C is 1. Thus, we can construct an XNOR gate by connecting the output A XOR B of an XOR gate to the input of a NOT gate. The output is A XOR B whole bar. The logic symbol of XNOR gate has bubble at the output of an XOR gate to denote the inversion. Like previous cases, we can have 3 inputs XNOR gate also. Let us now write the truth table for a 3 inputs XNOR gate. That is, in order of A, B and C, 0, 0, 0, D is 1, 0, 0, 1, D is 0, 0, 1, 0, D is 0, 0, 1, 1, D is 1, 1, 0, 0, D is 0, 1, 0, 1, D is 1, 1, 1, 0, D is 1, and for 1, 1, 1 inputs, D is 0. If we compare this truth table with that of an XOR gate, we find since the output D of XNOR gate is complement of the output D of an XOR gate, D is 1 when number of ones is even in the input bits. In other words, the output of XNOR gate is 1 for even parity of the input bits. For n inputs XNOR gate, the Boolean function can be represented as A XOR B XOR C and so on whole bar. If the output A XOR B of an XOR gate is connected to the input of a NOT gate, the output is A XOR B whole bar. The bubble at the output in the logic symbol of XNOR gate denotes the inversion. After having understood various gates and their characteristic features, we are now in a position to apply our understanding to the circuits meant for various arithmetic operations like addition, subtraction, etc. The simplest of such circuits is an adder circuit, which would perform arithmetic addition. There are 2 types of adder circuits, namely half adder and full adder. Let us discuss half adder first. Half adder is a logic circuit capable of adding 2 bits A and B. It returns sum and carry at the output. Thus, it is a 2-input and 2-output electronic device which performs arithmetic addition. At the inputs, it adds the bits A and B, and at the output, it returns the sum of A and B and the carry generated during this arithmetic operation. This is called half adder because it does not take a carry, if any, due to previous addition of 2 bits into account while adding A and B bits. To design an half adder, we first write a 2-variable input and 2-variable output truth table, giving us the correct sum and carry output bits. Using SOP method, we determine the Boolean expression for sum S and carry C. Accordingly, we draw a logic circuit with the help of required gates. Let us now write the truth table for an half adder. We know 0 plus 0, sum will be 0 and no carry is generated. 0 plus 1 equals to 1 without carry generation. 1 plus 0 equals to 1 and no carry is generated. 1 plus 1 is equal to 0, but a carry equal to 1 is generated this time. Thus, fundamental product corresponding to A equal to 0 and B equal to 1 is A bar into B for the sum. Similarly, fundamental product for A equal to 1 and B equal to 0 is A into B bar for the sum. Adding these fundamental products, we get Boolean expression for sum S to be equal to A bar into B plus A into B bar. As far as carry is concerned, there is only one fundamental product term, and that is A into B. Thus, Boolean expression for carry C is equal to A into B. Using SOP method, we can write Boolean expression for S and C in the following manner. S is equal to A bar B plus A B bar, and C is equal to A into B. Based on the Boolean expression for sum and carry, a logic circuit for an half adder can be drawn in the following manner. Connect A to input of a NOR gate so that the output is A bar. Add A bar and B to obtain A bar into B at the output of the AND gate. Similarly, obtain A into B bar at the output of the second AND gate, or the two fundamental products, that is A bar into B and A into B bar, to obtain sum S at the output, and A and B to obtain carry C. This completes the logic circuit of an half adder. Since the Boolean expression for sum S is the same as the output of a 2-input XOR gate, we can easily redraw the circuit using XOR gate and AND gates only. We have seen earlier that two binary bits A and B can be added using an half adder. Now, being a 2-input device, half adder cannot add 3 inputs. Therefore, it can be used to add either two single-digit binary numbers A and B, or the least significant bits, that is LSB, A0 and B0 of 2 or more digit binary numbers. This problem is overcome using full adder. Full adder is a logic circuit capable of adding 3 input variables A, B and C, and it returns sum and carry as the output. The third input C is the carry bit generated as the output of the previous arithmetic addition of lower order bits. This is called full adder because it takes a carry due to previous arithmetic additions into account while adding the input bits. Designing of a full adder is done in the same manner as for the half adder. That is, we first write the desired truth table, then determine the Boolean expression, followed by drawing the logic circuit. Now let us write the truth table for full adder. The inputs are A, B and C, where A and B are the bits to be added and C is the carry generated due to previous arithmetic operation. Addition of A, B and C should cause sum S and carry C0 at the outputs, and our desired truth table is 0, 0, 0 inputs. Sum is 0 plus 0 plus 0 equal to 0, and C0 is 0 as there is no carry generated. For 0, 0, 1 inputs, the sum is 0 plus 0 plus 1 equal to 1, and the corresponding fundamental product term is A bar, B bar, C, and no carry is generated. This time for 0, 1, 0, sum S is equal to 0 plus 1 plus 0 equal to 1, and the corresponding fundamental product term is A bar, B, C bar, no carry is generated. Therefore, C0 is 0. For 0, 1, 1 inputs, S is equal to 0 plus 1 plus 1 equal to 0, and a carry is generated. The corresponding term to C0 equal to 1 is A bar, B, C. Coming to the next term, 1, 0, 0, S is equal to 1 plus 0 plus 0 equal to 1, and the corresponding fundamental product term is A, B bar, C bar, no carry is generated. This time, next is 1, 0, 1. The corresponding S is equal to 1 plus 0 plus 1 equal to 0 and carry generated is 1. Therefore, fundamental product term corresponding to C naught is A B bar C. Next is 1 1 0 and S is equal to 1 plus 1 plus 0 equal to 0. Carry is generated. Thus C naught is 1 and fundamental product corresponding to C naught equals to 1 is A B C bar. Last combination is 1 1 1 and the sum S equals to 1 plus 1 plus 1 equal to 1. The corresponding fundamental product term is A B C and carry is generated this time, and the corresponding fundamental product term is A B C. Now using SOP method, we can write Boolean expression for S and C naught in the following manner. The expression for sum S has already been derived earlier as the expression for the output of a 3-input XOR gate, that is S is equal to A XOR B XOR C. Now let us determine the Boolean expression for carry. Adding the fundamental product terms in the carry column, we get C naught to be equal to A bar B C plus A B bar C plus A B C bar plus A B C. Rearranging the terms, C naught is equal to A bar B C plus A B C plus A B bar C plus A B C bar. Now taking B C common from the first and the second term, we can write C naught is equal to B C bracket open A bar plus A bracket close plus A B bar C plus A B C bar. This is equal to B C plus A B bar C plus A B C bar. In deriving this expression, we have reduced the Boolean identity, that is A bar plus A is equal to 1. Now taking C common from the first and the second term, we can write C naught is equal to C into bracket open B plus AB bar bracket close plus AB C bar. Now expanding B plus AB bar as B plus A into B plus B bar, we can write C naught to be equal to C bracket open B plus A bracket close into bracket open B plus B bar bracket close and bracket close again plus AB C bar, that is C naught is equal to C bracket open B plus A bracket close plus AB C bar. This implies C naught is equal to BC plus AC plus AB C bar. Further, C naught is equal to BC plus, taking A common from the second and third term, we can write A bracket open C plus BC bar bracket close. This is equal to BC plus A bracket open again C plus B bracket close into bracket open C plus C bar bracket close and bracket close again. This implies C naught is equal to BC plus A into bracket open C plus B bracket close. Rearranging, C naught is equal to BC plus AC plus AB. We further rewrite the same expression as C naught equals to AB plus BC plus AC. Thus, the Boolean expression for sum S is equal to A XOR B XOR C and carry is equal to AB plus BC plus AC. Now let us construct the logic circuit of a full adder. based on these Boolean expressions in the following manner. First, connect the two bits A, B and the third bit carry C due to previous arithmetic operation to the inputs of a 3-input XOR gate. The output of the XOR gate gives us the sum of 3 bits A, B and C, that is S equals to A XOR B XOR C. Now add AB, BC and AC using 3 2-inputs AND gates. Next, OR the outputs AB, BC and AC of the 3 AND gates to produce the carry C0 at the output of OR gate. Let us now summarize what we have learnt in this module. We have learnt in this module that a digital system can be represented by a logic system wherein voltage levels are represented by logic levels in terms of binary bits 0 and 1. A logical system consists of logic gates which are of various types, out of which NOR and OR gates are basic gates. Using these basic gates, other gates, that is NOR, NAND, XOR and XNOR can be constructed. We also understood the equivalence between NOR and bubbled AND gates and equivalence between NAND and bubbled OR gates. Through this module, we also learned to design adder circuits using SOP method. With this, we come to an end of this module. Thank you.